Welcome to ERC Tipsnology. In this video, we will be learning again how to do some calculations in a series parallel circuit. In this problem, we have R1 470 ohms, R2 0.2 kilo ohms, R3 100 ohms, R4 50 ohms, R5 50 ohms, R6 1 kilo ohms, and we have a voltage source of 25 volts. Now we are required to calculate for the following electrical quantities. First, we need the total resistance. We need to find the total conductance, GT. Total resistance is RT. We need to find the total current, IT. We need to find the total power, PT. The individual values of the conductances, G1, G2, G3, up to G6. The current through each of the resistors from I1, I2, up to I6. The voltages or the voltage drops on each resistors or across each resistors, V1, V2 up to V6, and the power dissipated or used by the resistors, P1, P2 up to P6. So to solve this problem, we have to analyze first the given values of the resistors and how are they connected. As shown here, we can see that the R1 is connected in series to R6. Therefore, we can add R1 plus R6. It's also clear that the R3, R4, and R5 are all connected in series. Therefore, we can add R3 plus R4 plus R5. And after doing that, we will have a single resistor here, which would be in parallel with the R2. Therefore, we can take the parallel of R2 parallel to the sum of the R3, R4, and R5. And after that, it will become one resistor. The R2, 3, 4, 5 will be in series with the sum of R1 and R6. Therefore, we can add R1 plus R6 to the parallel of R2 parallel to the sum of R3, R4, and R5. Now, let's do that in our solution. First, we need to write the circuit again. We have here R1 and we have here the R2. We have R3, we have R4, we have R5, and we have R6. Now the first thing to do to find the R total is to look up the series circuits or the series connections. So we have here the voltage source, of course. And as you see here, the R1 is in series with R6. And the R3, R4, and R5 are also in series. So we can calculate R16 equals R1 plus R6. And we will have, of course, we have the value of 470 ohms on R1. And we have 1 kilo ohm on R6. Therefore, we will have here 470 ohms plus 1 kilo ohm. 1 multiplied by 10 to the 3 ohm, or this is actually 1000. So 1000 plus 470, we will get 1470 ohms. And that will be our R16. Now for R3, R4, and R5, we can get the sum of the three, R3, 4, 5, of the three resistors, and we will write here R3 plus R4 plus R5. And then we will be adding the values of R3, R4, and R5, which are 100 ohms. We have here 50 ohms, and we have another 50 ohms over here. So we will have 100 ohms plus 50 plus another 50 ohms. We will get the value of R345 equals 100 plus 50 plus 50. That will be 200 ohms. Now we can draw again the circuit so that it's clearer to us. So we have here the voltage source, 25 volts. This is the VS. And then the combination of the R1 and R6, we call it R16 now, is connected to R2, still R2. But the R3, R4, and R5 will become one resistor now. And the name will be R345. And so you will see here that we only have 3 resistors. Now if you analyze this, R16 is in series with the source, and R2 and R345 are both connected in parallel together. So we can start with the R2345. We can say R2345 is the parallel of R2 parallel to R345. So this symbol means parallel. And so what's the value of R2? It's 0.2 kilo ohms before in the given. And so we will have 0.2 kilo ohms the formula for two resistors in parallel is this. This is the short way. R2 multiply it to the R345 divided by the sum of the two resistor. That's it. That's the formula. And so we will multiply R2 with the R345, which is 200 ohms, and divide it by the sum of the 0.2 kilo ohms plus 200 ohms. And there you go. We will have the value of the parallel of R2 parallel to R345. And our answer would be, let's calculate, 0.2 to the power of 3, because that's kilo. Let's write it here. 0.2 multiplied by 10 to the power of 3. But for those who can understand this, even without writing this, you may skip that part. But just to be clear about it, let's write the complete values of this. 0.2 multiplied by 10 to the 3 plus 200, so that it's very clear with you, or to you, what's the solution. And so, again, let's repeat. 0.2 multiplied by 10 to the power of 3 multiply with 200 equals divided by 0.2 multiplied by 10 to the power of 3 plus 200, close bracket or parenthesis. We got 100 ohms. So from here we can see that the R345 is 200 ohms, R16 was 1470 ohms, and the R2345 is 100 ohms. Now if you look at these two resistors in parallel and we draw it again, we will get like this a circuit. So let's put the plus minus again. Vs 25 volts, and we have here the R16 connected to the R2345, which will be represented by a single resistor now. So this is now R2345, and you can see here that they are connected now in series, right? And so we can say that the R total now of the whole circuit will be equal to the series of R16 plus R2345, because they are now in series. And so I will get the value of R16, which is 1470 ohms, plus R2345 of 100 ohms, and there you get it. So you got the number 1470 plus 100, that would be 1570, but just to be sure, let's say 1470 plus 100, we got 1570 ohms. This will be our R total. So our R total equals 1570 ohms. That's how to get the R total. Now to continue with the next problem, we will be getting the total conductance, GT. This is so easy, just divide 1 over the total resistance. So our total resistance is 1570. Therefore, we divide 1 divided by 1570. We would get 0. How many zeros is there? 1, 2, 3. 3 zeros, and then 6. 36942 Siemens. Okay, or we can say Mo, but we will just use Siemens, letter S. So our answer for the total conductance, we can just take 6 decimal places. 1, 2, 3, 4, 5, but because this is 69, we can round it up to 69.7, 637S, and this will be our GT, or the total conductance. I total, or total current, will be equal by Ohm's law. The Ohm's law is like this. The V, I, and R. We can get the I, V over R. So V over R. But because we're talking about the I total will be here, coming from the voltage source. So the I total will be equal to the voltage total, or the voltage source, Vs, over the R total, RT. That's what will happen. So our I total will be equal to the Vs. Our Vs is 25 volts, voltage source 25 volts, over the R total, which is 1570 ohms. And so we will get our I total 25 divided by 1570, we will get 0.015923.566, or we can just get 6 decimal places, and I'll just write here that our I total equals 0.15923, 0.01592, but 335.66, we can say 4, round it up, amperes. That's our total current IT. Now, if you want to calculate for the total power, we can calculate for the total power. How? We will just write the formula for total power. We can use VI. There's another formula for power. We can use V squared over R, or there's another one for the power. We can use I squared multiplied by R. Now take note that this is total power, so this will be total voltage or voltage source, and this will be the total current IT. And the R will be the R total, so this is I total, R total. That's what will happen. We can use any of these three formulas and we will get the same answer. Let's try it now. Let's do the first formula. Let's do the 25 volts multiply with IT of 0.015924 ampere, and our P total will be 25 multiplied to 0.015924. We will get 0.3981 watts. Okay, now let's try the other formula, Vs squared, or to the second power. So let's try 25 volts to the second power over the R total, which is 1570 ohms. We will get the value of the total power. Let's see the answer for this. 25 to the second power, where's the second power here, divided by 1570 equals 0.3980 0.89172. But look, if you check this, 3981, 3980, but if you round the 0.89, it will become 1. Therefore, PT is also equal to 0.3981 if you want to make it exactly the same with this. See? Watts. Same with this. But you don't need to use two formula. I'm just trying to show you that we can use either of the two, or either you use PT or you use VI, or you use V squared over R, or you use I squared multiplied with R. So either of these formulas we can use, whichever you like. Let's see the third one to prove that they will have the same answer. Our I total is 0.015924 amperes raised to the second power multiplied with R total of 1570 ohms. So we will get the same answer. What do you think? Let's see. 0.015924 raised to the second power multiplied with 1570, we will get the same answer, 0.3981 10828, right? But we can get 3981 here, so the PT is also 0.3981 watts, just like the other two formulas. So again, you may use VI or V to the second power over RT, or you can use I squared or I to the second power RT. That's it. That's how to calculate the total power. Now, moving on with the next calculation, we will calculate this time the values of the conductances. So the conductance formula is G1 equals 1 over R1. We will also calculate G2, 1 over R2. G3 is equal to 1 over R3. G4 equals 1 over R4. G5 equals 1 over R5. And G6 equals 1 over R6. The values of the resistors are the following. So we have R1, let's check here, 1 over 470. This will be 1 over 0.2 times 10 to the 3 ohms. And this will be 1 over 100 ohms. The fourth will be 1 over 50 ohms. Next will be 1 over 50 also. Then we have 1 over 1 kilo ohms. 1 over 470, I get G1 equals 0.002 1276. 1276, so we can make it 8768. Okay, this will be Siemens. Yes, and then we have G2 equals, you can also use mho, but we will use S or Siemens. Then we have 1 over 0.2, so 1 divided by 0.2 multiplied by 10 to the power of 3, let's put a parenthesis. Get 0.005. Yes, then G3 equals 1 divided by 100, you'll get 0.01. G4, 1 divided by 50, 0.02. And then 1 divided by 50, 0.02. That's G5. And lastly, G6 equals 1 over 1000, or 1 times 10 to the 3, 0.001. Yes. So other answers for the conductances. Now, going back with our solution over here, you can see that there's a current coming from the voltage source over here that will pass through the R1. Now, this current is called IT, right? And then at this point, letter A, it will be splitted into two, or divided into two. One current will go this way, and another current will go this way. Therefore, up to this point, this is the total current. Now, when it continues, it will go here to the I4, and then it will go through the I5, the R5. It will be I4 here, I3, I5, but they will have the same value because they are in series. And then when it reaches the point B, it will become together again, and that will be the same current with your I total because they are in series here, and this current will go back to our voltage source. And so we can say that the current IT is going through R1 and R6. Right? The current IT is going through R1 and R6. And because of that, we can say that the current on the resistor R1, by using Ohm's law, right? By using Ohm's law, we will get the current equal to V1 over R1, right? But we don't need to do that because the I1 will be equal to the I total because there will just be a single current in series. So in series, current is the same for all of the resistors. And we can also say that the current that will pass through the R6, which is I6, will be also equal to the I total. So I'll just write here 0.0015924 amperes. Also with I6, I'll write it as the same current. See? So we don't need to calculate I1 by Ohm's law, no need, because the I1 is the same with I total, I6 is also the same with I total. There will be a single current for the series circuit for R1 and R6. Now, it would be the same with R3, R4, and R5. Whatever current is going through here, right? This will be the same current that will pass through each of the resistors. So we will have here I3, we will have here I4, right? We will have I3, we will have I4, and we will have I5, right? But all of them, we can say that I3 will be equal to I4 will be equal to I5 because R3, R4, and R5 are in series, right? But we don't know what is I3, what is I4, and I5. But if you go back to our circuit number 2, we already got the R3, 4, 5, right? And there will be, this is point A, there will be a current over here. That current will be equal to the current I3, I4, and I5. But this current, we don't know the value of this current. But we can call this current as I3, 4, 5. Okay? That's what we will call it. And the current that will go here, we will call it I2. Now, the current that will go in or goes into the A, we will call it as IT. right? So by Kirchhoff's current law, all right, the current here, I345 plus I2 going out will be equal to the going in current, which is I total, by Kirchhoff's current law, right? The I345 going here will be equal to the I3 equal to the I4 and equal to the I5. That's what will happen. But we have to find the I345. Now, if you look at the circuit again, let's go back. Let's draw it again. You will have here the resistor R16 going to node A, and then in node A we have R2, and here we have the combination of R3, R4, and R5. So we call it R345, right? So let's draw it again here, and let's put the values here. Okay, there will be a current going in this way. We call this as I345, and there will be a current going this way, which we call I2, and there's a current going this way towards the node A, or the point A. We call it IT. Now take note, we have what we call as the Kirchhoff's current law, where we can say that I2 plus I345 equals IT. So that's Kirchhoff's current law. Kirchhoff's current law, I total equals the sum of I2 plus I345. Right? And we also have another rule, which we call as current divider rule. So we have what we call as the current divider rule. Okay. So for the current divider rule, we will consider the two resistors that we have here, the R2 and the R345. And we will just get the current of any one of these, whichever we want first. For example, let's try the I2. Alright, so for the current divider rule, you just need to write one letter R here, and then at the bottom you write R plus R. That's it. And then you multiply it with I. This is the current divider rule. Now the one you write at the bottom of the equation is just the R2 plus the R345. So it's so easy. Just write R2 plus R345, the two. But the one at the top that you will write must be the opposite resistor. So the opposite of R2 is R345. The opposite of R345 is R2. So if you want I2, you should write the opposite, which is 345. You got it? And the current that you will write here must be the one going into the node, which is IT. That's it. Now, in the case of I345, you may also use R over R plus R. Okay. Let's put a parenthesis here. Multiply with I. Now, again, just copy the R2 and R345. R2, R345. And the I total over here, the one going in. And the opposite current, I345. So the opposite resistor to R345 is R2. So that's why I will write here R2. And that's it. You can get the value of the currents by using the current divider rule. Okay, let's try it. Let's use I2 equals R2 plus R345. So that's how much? How much is our R2? 0.2 kilo ohms. And our R345 was 100 ohms. 100 ohms. And so we can write here 100 ohms, 100 ohms. Okay, so you see, I2 opposite R345, 100 ohms. Let's erase this. 100 ohms over the 0.2 kilo ohms. Okay, plus R345, which is 100 ohms. Multiply this to the I total, which is equal to, what's our I total? Where is it? Over here, 0.015924. 0.015924 amperes. Now for I345, we will be writing the same, 0.2 times 10 to the 3 plus, this is ohms, plus 100 ohms. And then the opposite of R345 R2, 0.2 times 10 to the 3, or that's 200. And then we multiply with the current, 0.015924 amperes. Okay? And so, we will get the value of I345, and we will also get the value of I2. So let's do it. Let's calculate the values of this. 100 multiply with 0.015924 equals, divided by open parenthesis 0.2 multiply by 10 to the power of 3 plus 100 close parenthesis equals 0.005308 amperes. Now the other one, open parenthesis 0.2 multiply by 10 to the power of 3 equals times 0.015924 equals, divided by the sum of 0.2 multiplied by 10 to the power of 3 plus 100 equals 0.010616 amperes. So that's our answer. Or, if you want, you may use Kirchhoff's current law for I345. If it is not required to use the current divider rule, you can use another rule, KCL, which is I total equals I2 plus I345. So if you already know the I2, you already know the IT, we can get the other current, I345, by simply subtracting I2 from IT. So we will write IT minus I2, and I'll get I345, right? So let's try it. Let's write the 0.015924 ampere minus the I2 of 0.005308 amperes. And what will I get? That's the, if I subtract the two, right? So let's see, 0.015924 minus 0.005308, we will get 0.010616 amperes. See? So we will be getting the same answer as the I345 over here. But of course, it depends if you are asked to use the current divider rule, or it was not mentioned to you what to use. You can use the Kirchhoff's current law in combination with the current divider rule. That's it. That's how to do the current for I345 and I2. So now I know my I345 is equal to 0.010616 amperes. And I know now the I2 is 0.005. However will I write it? I'll just write it here. 0.005308 amperes. That's for the I2 going here. Now if you add the two, it will be equal to IT, which is equal to 0.0159, right? 24 amperes. Okay? Now going back to our problem before, in the beginning, we have here, we say that I345 equals I3 equals I4 equals I5. And now I know the values of I345 is 0.010616 amperes. So it follows that my I3, okay, I hope that's clear. It follows now that my I3, let's include I2, that my I2 equals 0.005308 amperes, okay, and my I3 equals 0.010616. I4 equals 0.010616, and I5 is also equal to 0.010616 amperes. See, I2, I3, I4, I3, I4, and I5 are all equal to the total current through R345. So this is our conclusion, because the R3, R4, and R5 are in series, right? And so we now have our current. Now if we go back to I1, we have I1 equal to 0.015924 amperes, because this is the same as the I total, right? I6 is also equal to 0.015924, because the current in I1 and I6 is equal to I total, because the R1 in our original circuit, the R1 is in series with R6. And the currents I3, I4, and I5 will also be equal because they are all in series. That's why our answer here is correct, right? That's what will happen. And of course, we have the I total equal to 0.015924 amperes. So, in other words, by using the current divider rule, in using the current divider rule for these two parallel resistors, we got the answers for I2 and I345. And after that, if you go back in our previous circuit here, the current that will go here and the current that will go over here will also be the same. And this is the combination of R1, R6. So I1 and I6 are equal, and current total for 2, 3, 4, 5 will be equal to I total also. But this one is not series, right? The R2 is not series with the R345. R2 is parallel to the series of R345. That's what will happen there. So we got the I total now. And so if I try to, as you can see here, these are the answers. I1, I6, they are all the same with the I total. And then I3, I4, I5 are all equal because, again, the R1 and R6 are in series. Now, I3, 4, 5 are the same because R3, R4, and R5 are in series. Except I2, because I2 is not in series with the other three. That's why it's separated there. Okay? Now, the final thing that we will calculate, the final electrical quantity that we will calculate now is the voltage. Of course, also the power. Now, how do we calculate the voltages? It's so easy. Voltage 1 here, the voltage V1 here is like in series with the VS, right? And also the V6, the R6 is in series with VS, or our voltage source. So we can use the voltage divider rule. Voltage divider rule. This is for series, okay? For series only. The current divider rule that we use here is only for parallel. Because in series, the currents are the same. But in parallel, the currents are not the same because it will be splitted into two. So the total here will be the sum of that. Anyway, going back to our last part, Kirchhoff's voltage rule. And we have R1 and R6. R1 and R6 in series. So we can use the formula for voltage divider as equal to, similar to this, we will write V1 equals R over R plus R also, like that. And we will multiply it also with V. But the V that we will use here, like here, I total, we will be using V total or the VS. And the R that you will use here are the resistors, or the two resistors in series. Here, R16, and we have the R1 and R6. But we have to consider also the R2, 3, 4, 5. That's what we will do. We need to consider the total resistance of the three resistors. If we have three, but we have here we have to consider here R plus R, or we can say R total, not only like this. Okay, so this will be, if there's only two resistors, so we can say that V1 is equal to R over R total. No need to write R plus R, but instead we will write here R total. Okay, R total, and we will write V6 equals again R over R total multiply with VS. Now, if you go back here, we can see that the R1 is in series with our VS, in series with our R6. Therefore, R1 and R6 in series here, we can use the voltage divider formula. So let's try it. Let's do the voltage divider formula now. Which R will you put here? The one that you want. So if you want the R1, we will write R1. V1, we want R1. V6, we write R6. Okay, so V1 will be equal to R1, which is, what is our R1? 470 ohms divided by the R total. What is our R total? 1570 ohms. Okay, multiply with the Vs of 25 volts. Our Vs is 25 volts. And then for V6, we will get the R6. How much is our R6? R6 is 1 kilo ohm. So 1 kilo ohm, 1 times 10 to the 3 ohm, or 1000 ohm over the R total of 1570 ohm, multiply with our Vs of 25 volts. Okay? And we will get the answer of 470 divided by 1570 multiply with 25 equals 7.484. 7.484 volts. And then V6 will be equal to 1000 divided by 1570 multiply with 25. You'll get 15.92356 or 924 volts. And there you go, you got the voltage for V1 and V6. Now, if we want, we can get also the voltage of R2345. Because we got the voltage of V1 and V6, we can get the voltage of this 2345. So let's call it V2345. Okay? Now, how to get V2345? Same formula like what we did here. So we will get V2345 equals R2345 multiply with Vs over the R total. So we will have R2345 is how much? 100 ohms, right? So 100 ohms multiply with our Vs, which is 25 volts, over the R total of 1570. I will get V2345 equals what? 100 multiply with 25 divided by 1570, we will get 1.5923. So 1.59235. So 23524. Okay, 24 volts. And because of that, we can say that over here, R2 and R345 are in parallel, right? In parallel. So we can say that the V2 is equal to V345. All right. But the total of the voltage here is called V2345. Therefore, this is equal to V2, this is equal to V345. Again, the total voltage of these two, they are in parallel over here, will be equal to V2345, which we already know. All right. Therefore, I can say now that the V2 here equals 1.5924 volts. Okay? And I can also say that the V345 equals 1.5924 volts. Now, this V345, we will use this in our original circuit because, as you can see here, the R345 here is the combination of the series of R3, R4, and R5. Therefore, there will be a voltage here which we call V345. And I already know the V345 as 1.5924, right? So the V345 is 1.5924 volts already. And that will be the total voltage of the three resistors R3, R4, and R5. What I mean is V3 plus V4 plus V5 will be the total voltage V345. So if you think about it, we can say that V3 plus V4 plus V5 equals V345. That's what I'm saying, because R3, R4, and R5 are in series. And because of that, we can apply this rule, which is the Kirchhoff's voltage law, where the sum of the voltage inside the series circuit will be equal to the total voltage, if there's no other voltages. But because there's another voltage there, we will just call this not Vs, but V345. That's what will happen. Now, it will be 1.5924 volts equals V3 plus V4 plus V5. But the problem is we cannot do this because we don't know each of the values of this. So we will use the voltage divider rule again. voltage divider rule. And what's the voltage divider rule? V3 is equal to R3 over the R total of the 3, the 4, and the 5, plus or multiply with the voltage of this 3, which is V345. That's the special formula that we will do. And so we will get here the value of R3, which is 100 ohms, divided by the R345, which is 200 ohms, multiply with V345, which is equal to 1.5924. You already get V3, right? Here, you'll get the V3. Okay, now V4 will be equal to the same, R over R total multiplied to V345. I cannot write Vs because we're considering only the 3 resistors over here, R3, R4, and R5. It's like a separate series circuit. That's why I cannot use the Vs, because we are analyzing the R3, R4, and R5. And so we will have here R4, okay, multiply with our VR35. And for V5, the same. We will have R5 multiply with V345 over the R total. And we will get here R4. What is our R4? R4 is 50 ohms. Multiply with 1.5924 over the R total of 1570. And we will get our V4 here. I'll calculate later after I wrote the formula. Now let's continue with V5. V5 will be equal to our R5. What's our R5? R5 is 50 ohms. Let's multiply it with our V345 of 1.5924 volts over the R total of 1570 ohms. We'll get the value of V5 also. Now, by rule of mathematics, we can cancel the ohms here. We'll cancel the ohms here, and we'll cancel the ohms here. That's why the answer will be volts here. The unit. Don't forget the unit. Now, let's calculate. Okay, 100 multiplied to 1.5924 equals, divided by 200, we'll get 0.7962. Okay. Then the other one, 50 multiply with 1.5924 equals, divided by 1570, we will get 0.050713. 375, but I leave it there. Then we have 50 multiply with 1.5924 equals 79.62, divided by 1570, we will get 0.050713 volts. Now you will see that V4 and V5 are equal. You may wonder why, but look here, the resistance of R4 is 50 ohms and the resistance of R5 is also 50 ohms. That's why they have the same voltage. In series, when two resistors have the same resistance, they will also have the same voltage. In series also, even if you have different resistances, the current will be the same because there's only one current in series. Anyway, we have the V4, we have the V5, do we have the V6? The V6, we got already the V6 over here, so I think we're done. Let's just write all of our voltages. We have V4, V5, V3, we have V1, we have V2, V3, V4, V5. Let's put V6 over here just to make a summary. So our V1 is 7.484 volts. Our V2 is 1.5924 volts. And now you will see that 1.5924 is equal to V345. You know why? Because the resistor R2 is parallel with the resistor R345. Therefore, when two resistors are in parallel, the V2 and the V345 will be the same because they are in parallel. And look over here, we got V2 1.559 and also V345 1.59. That explains the reason why they are equal. And then V6, of course, V6 is here, V6. So how much is our V6? It's 15 volts. 15.924 volts, our V6. 15.924 volts. Now you will also say that, you might also say that, why is the V6 so big? 15, the others is only 1, this is 7, this is very small, less than 1. Why? Because the R6 is equal to 1 kilo ohms, right? The R6 is 1 kilo ohms, and if you compare this with the other resistors, 470, 0.2 kilo, 100, this has the biggest series resistance over here. The total of these resistors, R2, R3, R4, R5, is only, how much? 100 ohms, right? So if you think about it, if we analyze the circuit again as 3 resistors, there will be only 3 resistors in series here, like this. We will have R1, we will have R6, this is 1 kilo ohm, this is R2, 3, 4, 5, and so we will have R2, 3, 4, 5, 100 ohms, all right? And then R1 is only how much? 470 ohms. But the R6 is 1 kilo ohm. That's why R6 voltage V6 is very big, 15.924. Now, if you write the voltages here, this is 15.924, and our V235. How much is our V2345? How much is our V2345? Where is it? V2345 here, over here. Our V2345 is equal to 1.5924, right? And then our V1 is 7.484. Now, if you look at the voltage source, we have a value of 25 volts, right? Therefore, if this is 25 volts for Vs, if we want to get the total voltage Vs, it should be equal to V1 plus V2345 plus V6, right? Let's see what will happen. 7.484 plus 1.5924 plus 15.924. What do you think will be the total? Oh, you see, it's equal to 25. V12345 equals 25.0004, which is approximately 25 volts, and that's exactly the Vs here. Therefore, we can say that our answers are correct because we got the same total voltage for this. Okay, so now the last part actually is to calculate for the total power or the powers. Let's see. PT equals, let's use the easiest one, VI, right? VS IT. So our VS is 25 volts, multiply with the IT of, how much is our IT? IT is points, is this the I total? Where's my I total? Here, 0.015924. 0.015924 amperes. So our PT will be equal to how much? 25 multiply with 0.015924, you will get 0.3981 watts. Now P1, P2, P3, P4, P5, P6 will all follow the same formula. VI, V1 I1, V2 I2, V3 I3, V4 I4, V5 I5, and V6 I6. I have shown you before in the other example that we can use the same, we can use 3 formulas for our voltages, but I'll be using only this formula, VI, which is easier than the other 2. So if we will analyze this, what's the value of our voltages? Here we have the V1 7.484. Let me write all of them. We already get here 0.3981. Now let's try the others. watts. As you can see, the P6 has the highest power also, simply because the R6 has the biggest resistance of 1 kilo ohms. And so that's it. These are the answers that we got from our calculations. So again, let's summarize what happens here in this circuit. What happens in this circuit is that the R total is equal to the series of R1 and R6. Okay. And series with R2, 3, 4, 5 plus the series of in series with R2, 3, 4, 5. But remember, R2 is parallel with 3, 4, 5. So we will say R2 is in parallel with the series of R3, 4, 5. So this will be the relationship. Okay? This will be the relationship. This is series. This is also series. But the R2 is parallel with the R3, 4, 5. And all of this will be in series with the series of R1 and R6. That's the relationship between all the resistors. That's it. That's the main. Now remember that if your R total is wrong, okay, I think everything will be wrong because the G total depends on R total, 1 over GT, and the I total depends on the R total also. The power will depend on which formula you used, whether you used, again, we have 3 formula, VI, you used V squared over R, or you used I squared multiplied by R. You see here, if this is the power total, this must be the VS, this is the VS, it's fine. But if you use the second formula and your R total is wrong, this will be wrong. If you use the third formula and your R total is wrong, this will be wrong. Now, you may say that if you use the I total or the current here, it will not be wrong. But remember, the I total is equal to the voltage source divided by the R total. So again, if your R total is wrong, this will be wrong, this will be wrong. Okay? Now, maybe you will be right with the other values of like G1, G2, G3, G4, G5, G6 because this is only 1 over R. 1 over R1 plus 1 over R2. So it's easy because the resistors are all given. Maybe here you will not have a problem. Now, when it comes to the I1, remember that I1, right? The I1 and the I total is the same. So we will say I1 equals the I total. And here, it's also I total, right? And it will pass through the I6. So the I6 is also equal to I total. But over here, if you will say that I2 equals I total, right? This is wrong. Why? Because there's a point here or a junction where your I total will not be going here and become I total also. No, it will not. Why? Because there will be another current over here that will go to I3 or to R3. And this current here will be called I2, right? Therefore, the I total will be not equal to I2. It will be the sum of I2 and I3. That's what will happen there. Now, going here, the I3 will be the same with the I4, and it will be the same with the I5. Because the R3, R4, and R5 are all in series. And we can call it I345. Okay? So that's what happened in our circuit. That's why if you will think about it, right? If you will write the circuit again, from here, from 2 resistors, or how many? 6 resistors. This is series. This is also series, right? And what happened? It becomes 1 resistor. And this also becomes 1 resistor. This becomes 1 resistor. That's what happened. Correct? Now, if you look at this, this is the basic 3 resistors in series parallel. So if you know how to do this, then you're done with your calculations. Why? This will be parallel, right? And if you do it, if you continue to do it, the parallel will become 1. And now what do you have here? It will be series. So you will just add this plus this, you will get the R total. That's the idea over there. So be careful with the calculation of the R total. If the R total is wrong, I total, which is Vs over RT, will be wrong. And then if you have the current over here, IT, and it's wrong, then how will you use the current divider rule? Remember the current divider rule. The current here on the right, let's call this what, 3, 4, 5. So this is R3, R4, R5. So this is R3, 4, 5, right? And this is R2. So current divider rule, I want I2. Again, let's do a revision. R over R plus R multiply with I. The I going here is IT. And the R2 plus the R3, 4, 5. That's it. That's the formula. Now, what will you write here? If you want I2, take the opposite. So, we'll write here 3, 4, 5. Now, on the other hand, if I want I3, 4, 5, I want I3, 4, 5 here, the current here. I will take the same formula, R over R plus R. This is R2 plus R3, 4, 5. And this will be the opposite. What do you want? I3, 4, 5, right? What's the opposite? R2. So, you write R2. And then you multiply by I total, and you will get the I3, 4, 5 and the I2 by current divider. Now, for the voltage divider here, this is actually R1 and R6, right? So this is R16, and this is R2, 3, 4, 5. Now, this is series. Therefore, if I want V16, that will be equal to R over R total multiplied by Vs. And then V2, 3, 4, 5 is equal to R multiplied by Vs over R total also. And the R here will be the R16. And the R here will be the R2, 3, 4, 5. And you will get the V16, you will get the V2, 3, 4, 5. This is called the voltage divider rule. Okay. Anyway, everything is here. We have started from this page, and then I showed you from the beginning how to do the calculations of the resistance, of the conductance, of the current, and of the power. All the calculations are here, and if you watch this video again from the beginning, you will be able to see how these values were taken or calculated from the given values or from the given problem. Okay, so thank you so much for watching this long video tutorial about the series parallel circuit. I hope that you will be ready to whichever purpose you are watching this video about the series parallel circuits, especially for those students who are watching right now, who are beginners in series parallel. I hope you understood what I have shown you and appreciate it, and please subscribe to our channel. Have a nice day, everyone.